What I'm going to tell you about today is work that I think is very important. I'm going to try and justify why it's important and why the approach I'm going to describe is interesting. And just 5 minutes ago, I discovered there's some work on high-temperature thermoelectrics going on in this department. And because he's recently been made an associate professor, I wasn't allowed to meet him. I'm allowed to meet assistant professors. But never mind. Let's see if I can turn this on. So this is the title. I've attended a number of lectures over the years by distinguished lecturers, especially when I was younger. And I always found that they were, at the end of the talk, I didn't really know what the talk was about. So I hope that's not the case here. But to give you an excuse, I'm going to tell you the main takeaway messages that my talk's about. So if you want, go out and get a cup of coffee or a cup of tea after I've given you this. So most of you already know this, but just in case there are some people here who don't, that thermoelectric materials and devices are an efficient way of directly converting heat to electricity or vice versa. I want to give you a rationale for working on high-temperature thermoelectrics. This isn't a very popular field, but I want to persuade you, or at least put the evidence in front of you as to why it's important. I'll say a little bit about the current status of thermoelectric materials. I also want to make a point that it's very important to start thinking nowadays of making materials from earth-abundant elements. And you'll see why, or at least I'll try to persuade you why that's important. Also, I want to explain why many of the current approaches to making high-efficiency thermoelectrics are doomed to failure at high temperatures. And so we need a different approach, and that's what I want to describe. And I will describe that in terms of what I call natural superlattice oxides. These self-assemble at high temperatures, and they're resistant to coarsening, which we'll find to be very important. And then, if I have time, I'll talk about some of the opportunities for new physics in these materials. So let me start by giving some perspective. As graduate students, it's very easy to get caught up in your own research, and your advisor tells you that your research is very, very important. But sometimes it's important to put your work in context of a larger issue. So that's what I want to try and do today. So here is some data. It was published by, I'm still learning how to use this, published by Mike Ashby in 2009. So it's a little out of date. But it's the world's energy sources as of 4 or 5 years ago. And it's a plot of world energy consumption, either in attajoules per year or kilowatt hours per year, on a logs plot for different sources of energy. On the left-hand side, we have energy from fossil fuels, coal, oil, gas. You can see they're by far the largest. Then there's energy that's derived from some form of solar energy. So one is energy associated with hydropower, one with wind, one with solar. You can see there's roughly an order of magnitude between each of these. By the way, this is solar heating. This is just warming up hot water. Photovoltaics are down here together with tidal and wave. And then on the right-hand side, we have energy sources from nuclear and geothermal. I think if you hadn't seen this and I asked you a question, how large was solar or how large was tidal energy, you'd think that they were much larger than they are shown here. But even if photovoltaics increases at 10% a year, it's still going to be many, many years before it replaces coal, for instance, or oil. The other point I want to make in this slide is that something like 60% of all the world's energy consumption is wasted or converted into heat that isn't useful. And you might argue whether it's 50%, 60%, or whatever. It's still an enormous number. So there's a lot of activity around the world to try and make machines more efficient. And in fact, one of Professor Liu's and my own interest is in trying to make the gas turbines more efficient. But today I want to talk about a form of recovery of waste heat that isn't really shown here because it's a secondary effect. So that's the world's energy sources as of fairly recently. The other thing I want to do to put things in perspective is ask, in the last 200 years, 300 years, where have all the scientific inventions come from that impact energy use and consumption today? So the 19th century, we can start with steam engines, diesel engines, fuel cells, light bulbs, thermoelectricity, and piezoelectricity. These were all discovered in the 19th century. If we look at the 20th century, we see, by the way, this isn't meant to be an inclusive list, but just the main areas: superconductivity, fusion and fission, practical piezoelectrics, practical ambient temperature thermoelectrics, gas turbines, PN junctions, lithium-ion batteries. If we go to the 21st century, I'd ask you to suggest what revolutionary new invention there's been in the 21st century. Anyone got any ideas? I don't know of any. You might argue that biofuels, for instance, and more efficient ways of converting organic materials into fuel would be one approach, but it isn't clear that's right. So the net result is that we're going to have to use one of these existing forms of energy generation for years to come. There's another important thing that's happening in the energy field, and I apologize if I'm telling you things you already know, but one thing is that there's, of course, now, by virtue of the development of solar power, local power, excuse me, this has gone ahead, the development of power at the local level. This is very important in the underdeveloped world, as you can imagine. That this is really a trend that's happening, this local power versus electrical grid power. And for electrical grid power, I've chosen this solar thermal power plant in Nevada. It's just the border of Arizona and New Mexico, Arizona, California. This is one of 3 stations that together give them 377 megawatt of electricity. By the way, this cost about $2 billion. Just in case you're interested. The other trend, of course, is that we have an enormous number of mobile devices, and it's only seen that there are going to be more and more of those. There's a lot of alternative ways of powering these, ranging from capturing Wi-Fi power, thermoelectrics associated with the body, etc. And then there's a large development of off-grid local power. For instance, in transportation systems, or in refineries, or in car engines. This is what you really need, some local off-grid power. This, by the way, is a gas turbine. If I was standing here, and I obviously couldn't take a picture at the same time as I was standing there, I'd be about the height of this. That produces about, I think, 50 megawatts, 60 megawatts. So this is the area of perhaps this room here, this cross-section area, and that produces roughly 1/6 of this activity up here. So we're going to see more and more off-grid local power as time goes by. So thermoelectric devices were first discovered in 1821 by Seebeck. And just for curiosity, I went back to the original work. This is the front page of his book. I don't think many of you know how to read German, but this is, he called it magnetized polarization. And what he discovered was that if he had a temperature difference across a wire or a beam of material, he'd generate a voltage. He misinterpreted the origin of that voltage, but nevertheless, even though he had the wrong explanation, he had the right measurements, namely that the voltage you could generate was proportional to the temperature difference across the material. He used metals, and is proportional to a constant known as the Seebeck coefficient, depended on the material. We now know it depends on how the material is processed and all sorts of other characteristics. The advantage is that these devices to generate voltage from temperature difference are solid state and they have no moving parts. And just for illustration, this is actually a thermoelectric cooler. It's just operating the other way around. And this is about, say, 2 millimeters high, and it will operate for 20 or 30 degrees across it. The other thing you need to know is a comparison of the energy efficiencies of different power generation technologies. So this is a plot of power generation efficiency, all the way from 0 to 100% up here, as a function of the heat source temperature. So the granddaddy curve on here is this one. It's the Carnot cycle. And as far as I know, there's only one energy source that has efficiency greater than the Carnot efficiency, and that's a fuel cell. Then these red targets are roughly the power generation efficiency of different technologies associated with different source temperatures. So these are fuel cells, these are geothermal. They're all relatively inefficient devices. This is a class of thermoelectric materials that has a parameter that I'll come back to later, ZT being a half. To get up to a Carnot efficiency, you need a ZT of about 30%. Now, nobody at the present time is suggesting you can get that with thermoelectrics. But the important thing in all these curves is the higher the temperature you operate at, the higher the efficiency. I will show you that many materials that are presently used for thermoelectrics will melt or decompose at temperatures around here. So in order to get benefits of higher temperature, you have to go to different materials. And you might argue, well, why do we even worry about thermoelectric materials? Or the efficiency in particular. The first is that you'd like to have a use of a thermoelectric generator that will produce power over long periods of time. Then the fact that you don't require any moving parts means you don't have to worry so much about maintenance. I'm going to argue that since oxides are stable in air, they can be used at high temperatures without complex packaging. And if you look at modern thermoelectrics, packaging is absolutely crucial. With oxides, you will need less of that. Many of these materials I'm going to describe are earth abundant, so the cost is relatively insensitive to the markets. I'll describe how I interpret that in a moment. And you can argue, or some people may argue against you, that because it's waste heat, it's free. But at least it's cheaper than if it's a primary energy source. So where are some examples of high temperature that we might be able to utilize? One is in exhaust manifolds of combustion engines or buses or some other. So this is a real picture of an exhaust system for this particular manufacturer's car. And everything that's appearing red is above 800 degrees Fahrenheit. So the problem here is that, of course, this is a complex geometry, and you wouldn't be able to introduce a more simple one because those geometries are dictated by the efficiency of the engine and fluid flow. So you'd have to have converters that will convert heat over these complex shapes. There are chemical plants that have literally kilometers of piping. In fact, one of the interesting things about chemical plants is in some areas of the plant, you have to heat the pipes. In other areas, you have to cool them. So there's really, if you could take advantage of the heat in some areas to generate power that you could use for cooling, there would be a real advantage. And there's activity along those areas. And then you could look at, I've listed a number of other examples where we have high temperatures. By high temperatures, I'm really arbitrarily saying a high temperature, say 800 degrees C and above. But it doesn't really matter exactly